In Chapter 4, Notes B, we're going to go over shapes using the Vesper theory and polarity. The presence of different types of bonds and lone pairs is actually what drives the shape of the different molecules and their polarity. The first thing you should know about bonds is not all bonds are created equal. Bonds can have different lengths and strengths depending on whether they are a single, double, or triple bond, and depending on which atoms are involved in the bond. Let's start with the fact that there is a force of attraction between the protons in the nucleus and the electrons in the bond. That attraction would be increased if I had more electrons involved. More electrons involved means more total attractive forces overall. So if I have more electrons, that bond will become stronger and therefore shorter. So your single bonds would be your longest bonds and your weakest bonds, where a double bond would be stronger and shorter. The triple bond would then be the strongest and actually then the shortest bond that there is. Let's look at some trends using some specific examples. First, we're going to break this table down to compare single bonds, double bonds, and triple bonds. Let's start with the length column. The single bonds have the longest bond, and as you go down to double and triple bonds, the triple bonds have the shortest bonds. If you look at the strength column, you're going to see exactly the opposite. At the top of this table, the single bonds have the weakest strength, and it increases as you build up to the triple bonds, which have the strongest bonds. So the pattern we see here is that as you add more electrons to the bond, that bond becomes shorter and stronger. Now let's compare some atoms that have the same type of bond to see how the type of atom can actually affect the bond length and strength as well. Let's first look at our two single bonds, chlorine and carbon. The chlorine is going to be found in the third row of the periodic table, whereas the carbon would be found in the second row of the periodic table, meaning their electron configurations would show that carbon has electrons in the second energy level and chlorine has electrons in the third energy level. The outermost energy level is going to be what is involved in a bond. Those are your valence electrons. So the chlorine valence electrons are located further from the nucleus, would experience more shielding, would experience less attractive force overall. So that bond is going to be weaker and longer than carbon's stronger and shorter bond because it is further from the nucleus. Let's compare our double bonds to each other or our triple bonds to each other to see what happens when the atoms actually are in the same row of the periodic table. Carbon, oxygen, and nitrogen are all found in the second row of the periodic table. They all have a valence shell in the second energy level. So what matters now is the attractive forces. Carbon's atomic number is 6 and oxygen's atomic number is 8, meaning that carbon has 6 protons and oxygen has 8 protons. More protons will be better at pulling the electrons. So you would have a stronger bond in your oxygen than you would your carbon. You're going to see the same pattern comparing carbon to nitrogen. Carbon has a atomic number of 6 and nitrogen's atomic number is 7. So again, 7, the nitrogen, would have more attractive forces and a stronger pull. So you're going to see an increased strength compared to carbon's strength and a shorter bond compared to carbon's bond. And that will be the general pattern if you're comparing atoms that are in the same row of the periodic table or have the same valence shell. We do have a little anomaly here where our strength kind of seems to go against trend with the double bonds, but you do see the shorter bond where the oxygen has more pull, so that still follows the trend. Notice the factors affecting the length and strength of bond are the same type of factors that affected our periodic table trends. Things like distance from the nucleus and nuclear attraction also affected your electronegativity and your ionization energy. So these are the types of things that affect particle motion, whether those particles be atoms themselves or the subatomic particles like the protons and electrons.
Another thing I want to comment on here is that this is not a linear progression. Just because I have twice as many electrons involved does not mean I double the bond strength. I mean, think about it. You are not doubling the number of protons. You're not doubling the overall attractive force. You're just adding more electrons, and so it is a stronger attraction. There is more of an attractive force, but it is not linear. So it would be incorrect to try to say it's 2 times or 3 times as strong if you have a double or triple bond. Onto valence shell electron pair repulsion, or VESPR theory. Valence electrons are, of course, in the outermost shell, so as the name implies, the electron pairs are in the outermost shell, and we're going to be looking about how repulsion, that's the most important word there, repulsion drives the shapes of the molecules. There are several things you should know about VESPR theory before you try to actually apply it, so we're going to go over a few of those key points. First of all, there is actually repulsion between both bonding and non-bonding electrons. Now, non-bonding electrons are the most aggressive, and those are the ones I emphasized the first time you went over some of the basic shapes. But as it turns out, bonded electrons, or the dashes when you draw the Lewis structures, the actual shared electrons, they're negative as well, and so they will also cause some repulsion. But they do act as a unit. So if you have a double or triple bond, that's going to behave as a single unit. And that is known as a negative charge center. That's a term you're going to hear a lot, charge center. An area where the charge is acting as one whole unit. So let me give you an example. Say we're looking at carbon monoxide, which would have a triple bond with 2 lone pairs. Each lone pair would be a charge center, but then the entire triple bond would act as a separate charge center, but a unified charge center, for a total of 3 charge centers in the entire molecule. Quick note, this is just an example of how to look at the total number of charge centers in an entire molecule, but when we start talking about shapes, we're going to be interested in a central molecule and how many charge centers it has. This example doesn't have a central molecule, but it does show you that the bond acts as an entire unit, a single unit, when you're counting charge centers. And this actually leads perfectly into the next point, that the total number of charge centers will determine your geometrical arrangement, also known as the shape of the molecule. So it's going to be determined by not only how many atoms are attached, but also how many lone pairs are attached. That being said, keep in mind that the non-bonded pairs of electron, also known as lone pairs, in other words, the dots, not the dashes, they would have a greater repulsion, more repulsion than the bonded pairs. And so they are typically the more aggressive in driving the shape. They're going to change the bond angles differently than a bonded pair would. So let's start comparing these differences, starting with 2 bonding pairs and the repulsion between them. Bonded electrons would be represented as dashes in the Lewis structure. So when you're looking at the repulsion from these sets of electrons between the 2 hydrogen-oxygen bonds, that repulsion is the weakest of our 3 options. The next strongest would be between a lone pair and a bonded pair. So in between the bond of a single oxygen and hydrogen and one of its lone pairs. That would be the lone pair to bonding pair repulsion. The strongest repulsion of all is between 2 lone pairs. Lone pair to lone pair repulsion is going to drive the shape the strongest. It's going to push the hardest and be repelled the most. Let's look at how that affects the shape. Here I have 3 different examples of molecules that have 4 charge centers. So first, to recap a charge center, that would be any area of electrons around my central molecule. So I have in my methane 4 bonds. For my ammonia, I have 3 bonds and a lone pair. And for my water, I have 2 bonds and 2 lone pairs.
Now let's look at how the different types of charge centers can change the angle. The basic shape for four charge centers is tetrahedral, which we have here with methane. In methane, we have all bonded to bonded interactions. So the typical bond angle would be 109.5 degrees. This would represent those four attachments, those four bonds being equal distant apart from each other. So there would be 109.5 degrees in between any two hydrogen carbon hydrogen angles. If I look at ammonia, now I have introduced a lone pair. So now you're going to have a lone pair to bonded pair interaction, which is a greater force of repulsion. And so that's going to act to close the gap between the two hydrogens. So the hydrogen, nitrogen, hydrogen angle would be only 107 degrees. As we go over to water, now we have two lone pairs. So not only do you have some lone pair to bonded pair interactions, which are of greater force of repulsion than between the two bonds, but you also have the lone pair to lone pair interaction, the greatest force of repulsion. So that's going to act to close the gap between hydrogen, oxygen, hydrogen even more, decreasing the bond angle all the way down to 104.5 degrees. You do have to know the basic bond angle. So for tetrahedral, you should know it's 109.5. You do not have to memorize all of the varying degrees, but you should know the pattern where if I have a lone pair to bonded pair interaction, it would decrease it. The more of those interactions, and including lone pair to lone pair interaction, would decrease it even more.
So what we're really going to see here is that the non-bonded pairs of electrons are the most powerful influence of the shape. However, they are left off when you name the shape. The geometry of the shape is based on the atoms. It completely ignores the lone pairs. But you better think about them when you identify the shape and when you determine the bond angles. So let's get into some of the shapes. The first shape we're going to look at is linear, where our central molecule has exactly two charge centers. So those two charge centers would 180 degree repel each other. So you have this linear shape. This means that there are not lone pairs on the central atom. So some examples, even carbon monoxide, if there's two atoms, it would still be considered linear, or carbon dioxide, since it has a double bond on each side, that would also repel 180 degrees and be linear. Notice the lack of lone pairs on the carbon. And if you have two charge centers around a central molecule, this is your only shape option. So now let's look at some options for shapes if there are three charge centers. So the first is the trigonal planar shape, which occurs when all of the charge centers are in bonds, in which case the bond angle would be 120 degrees. In a trigonal planar shape, those bonded pairs would be equally repellent of each other. However, if there is a lone pair instead, remember that the lone pair to bond interaction is more repulsive, and so that pushing coming from the lone pair is going to decrease the bond angle. The name of this shape we usually call bent. IB likes to call it V-shaped. I've also heard it called angular. But what you should know most importantly is that the bond angle decreases because of these lone pair repulsions actually.
Now let's look at our options when we have four charge centers. The basis for this is the tetrahedral shape, which would have bond angles of 109.5 degrees. All of the atoms in the tetrahedral shape are connected with bonded electrons. So we have all bonded interactions, bond-to-bond electrons that would evenly repel each other. So we have a uniform bond length of 109.5 degrees. If instead of all bonded electrons, I introduce one lone pair, now I have a lone pair to bonded pair interaction. These interactions between the lone pair and the bonded pairs are going to push the atoms closer together. And so we would decrease our bond angle less than 109.5 degrees. If I actually have two lone pairs, leaving just two bonded pairs for our bent or V shape, those lone pairs are pushing against the bonded electrons, and the lone pair to lone pair interaction is extremely repulsive. So we're going to greatly decrease our angle. You may recall that we used these three shapes earlier when we looked at the exact bond angles, and we saw tetrahedral was 109.5, pyramidal was 107, and the V shape or bent shape was 104.5. Again, you don't have to necessarily memorize those numbers. So another way to kind of show that you understand that the V shape is pushed even more so than the pyramidal shape is by using two less than signs in front of it. And that's the way that you're going to see it when we look at a table in a few minutes. So we have 109.5 for the tetrahedral, less than 109.5 for the pyramidal, and even less than 109.5 for our V shape.
Now let's take a look at some shapes for some expanded octets, which we have recently learned most of the atoms on the periodic table can actually have. So if I look at the basis for the 5 charge centers, we would see that there's basically a triangle connecting 3 that kind of reminds me of that shape of the trigonal planar, where I have those 3 equidistant would be 120 degrees away from each other, those atoms surrounding the central molecule. And then straight up and straight down, 180 degrees from each other and 90 degrees from the nearest atom, we would have the other 2 charge centers. So across the triangle, the bond angle is 120. And then from that plane down or up, that would be 90 degrees. The basis of that shape, we call that shape bipyramidal. And as we go into some other shapes we can form with 5 charge centers, this is the shape that we'll modify. Let's start with removing one atom and creating a lone pair there. That shape was then called a seesaw. It's easier to see where you get its name if you tip it on its side. The atoms in the plane with the lone pair create the feet of the seesaw, and then the up and down, as we referred to them before, atoms now have 180 degrees from each other would be the plank of the seesaw. If I remove 2 atoms and have 2 lone pairs instead, we call that the T shape. You still have 180 degrees between your up and down atoms, and then you would have 90 degrees between one of the planar atoms and the up or the down atom. And so that creates literally a perfect T between the up and down atom and one of the atoms in the what used to be the trigonal planar part. And again, it is a little easier to see if you tip it. So we would have our 2 lone pairs out here to the side pushing this bottom atom away. If you have 3 lone pairs, then the other 2 atoms would just be your up and down atoms. There would be a 180 degree separation then from the attachment to the other attachment. So we would call that a linear shape. And last but not least, we're going to look at 6 total charge centers. The basis of this shape is known as octahedral. So if you had 6 atoms attached to the central atom, we would call that an octahedral shape. And this equidistance then would all be 90 degrees. The atoms in the plane would create a perfect square, and from corner to corner would make a 90 degree angle. And then from top out to the side of the plane would also be a 90 degree angle. So this is 90 degrees overall, octahedral shape. If you have 1 lone pair, it would be removed from the up and down part of the molecule, and so you would still have all 4 of the plane that would then also still have an upward connection to one of the atoms. We would just be missing the bottom part of the pyramid. And of course you could flip this upside down and say it inversed. But basically, we're making a pyramid, but it is different from the trigonal pyramid we referred to before. Now it has a square base, and so we call this a square pyramid, where there are 5 atoms attached, but they form a pyramid because of this lone pair. If we removed 2 atoms and had 2 lone pairs, we would then just have this planar shape, the square shape. This would still have a 90-degree repulsion from each other because they're still all in the same plane. They would be forced into that same plane because of the repulsion of the lone pairs. Let's focus on the last 2 shapes for octahedral before we look at the big picture. They're shapes we've already mentioned actually. So if I remove 3 electrons, instead of taking from the top and the bottom, I would actually be removing from the plane. Or I'm sorry, if I was removing 3 atoms and putting in electrons. So that molecule shape then would just be the T-shaped, just as it was when I removed 2 from the 5 charge centers area. If I removed 4, I would remove the 4 from the plane and leave the up and the down, which would of course be your linear shape. Now let's look at this table as a whole. It's actually a really good way to summarize the different bond angles. 0 lone pair column would represent the basis of the shapes, where if I had 2 charge centers, it was based on the linear shape. 3 charge centers would be based on trigonal planar. 4 charge centers would be based on tetrahedral. Now the new ones, 5 charge centers would be based on trigonal bipyramidal, and 6 charge centers would be based on octahedral. Then you have to consider what happens as you add in lone pairs instead of bonded electrons. Now let's look at the bond angle as you go across the rows. So of course, if you have 2 charge centers, the angle has to be 180 degrees. If you have 3 charge centers, they would be evenly spread out at 120 degrees away from each other. However, if you have a lone pair, that would increase the repulsion, therefore decreasing the bond angle. So in a bent molecule, it would be less than 120 degrees. For 4 charge centers, the basis is tetrahedral, and the equal repulsion would give an angle of 109 degrees. However, if you add a lone pair, then that bond angle decreases. And if you had 2 lone pairs, it decreases even more. So the trigonal pyramidal shape has a less than 109 degree angle, and the bent shape would have even less than that. And that's actually the examples we looked at earlier when we compared water to ammonia to, I believe it was methane. As we move into the new shapes with the expanded octet, we have to consider the different repulsions between what I'm going to call planar atoms, or atoms that would be in the same plane. So for the trigonal bipyramidal, that would be the 3 that lay out flat with the central atom. And for octahedral, there would be 4 that lay out flat with the central atom. So I'm going to call those the planar atoms. And then the atoms that go up and down, I'm going to call the axis atoms. And that's a terminology I got from my college education. IB doesn't have a particular term for it. But I find it easier to talk about these things if we can have terms for them, so that's what I'm going with. So let's first focus on the planar atoms, for lack of a better term. In a trigonal bipyramid shape, there would be 120 degrees between them, just like the trigonal planar shape, because that's pretty much what we have in the plane. Now, if you add an electron pair in instead of a bonded pair, you're going to get more repulsion. And so you would get a smaller angle, less than 120 degrees. In the octahedral shape, the angle between the 4 corners would be 90 degrees. If you add in 1 electron, even though it's on the axis, it's going to force these atoms upwards, which actually means the distance between them is even less. They're not flat out on a plane. Picture taking a piece of paper and pushing the 4 corners upwards. That is going to decrease the distance between the 4 corners, and so the angle is then less than 90 degrees again. But the catch is, if you do that on both lone pairs, then you now have equal repulsion, and so you're back at a set 90 degrees. I also want to point out in the shapes at the end of these 5 and 6 charge centers, the linear shapes, that occurs because all of the lone pairs in the plane are equidistant. And so that would allow then the axial atoms to become linear. They would be equally repelled from each other at 180 degrees, even. You should know that, though, that the axial atoms distance from an atom in the plane can be affected by the other lone pairs. So if there are other lone pairs in the plane, that can actually decrease the distance between one of the axial atoms and the planar atoms. So like these two atoms right here would be more attracted to each other, or I should say more repelled from the other direction. So they would have a smaller angle. So you can see that if you add extra electrons in the plane, that can decrease the angle between the remaining planar atoms and the axis itself. Now I realize, especially towards the end, that's kind of a lot of information and it can get really complicated. So I'm going to try to highlight some of the most important things for you to know. For one, you should know the basis of the shapes based on the charge center. If there are two charge centers, it's based off a linear shape. As a matter of fact, that's the only option. If there are three charge centers, it's based off the trigonal planar shape. If there are four charge centers, it's based off the tetrahedral shape. If there are five charge centers, it's based off of the trigonal pyramidal shape. And then if there are six charge centers, it's based off the octahedral shape. That's the basis. You should also know the basis of the angles. A linear shape would have a 180 degree repulsion from connection atom X to other connection atom X, where E would represent the central atom. So basically it lays out flat, 180 degrees from attachment to attachment. If you look at trigonal planar, the attachments, or the X's, would be 120 degrees away from each other. If you have tetrahedral, then all of the atoms would be 109 degrees away from each other. So for linear, trigonal planar, and tetrahedral, there is 1 degree to know. But when you get to trigonal bipyramidal, there are two separate systems going on here. The planar atoms are 120 degrees away from each other, whereas the axial atoms and the planar atoms are 90 degrees away from each other. And then, of course, axial to axial would be 180 degrees away from each other. Octahedral, you have all of that going on, but it all kind of comes into harmony, where the square planar atoms are 90 degrees away from each other, as well as axial to planar atoms being 90 degrees away from each other. So it is a 90 degree overall. Like every atom is 90 degrees away from every other atom. Once you have the basic angle down, you have to consider that more repulsion would equal a smaller bond angle. So for example, with the three charge centers, although 120 degrees is normal for all bonded atoms, if you involve a lone pair, you know that lone pairs have greater repulsion to bonded electrons. And so the repulsion is going to push against both of those X atoms, and so those X atoms would then become closer together. And so you get this smaller bond angle. And if you have more repulsion, not only do you have more lone pair to bonded pair repulsion, you also have lone pair to lone pair repulsion. So it's going to even more push the X atoms together, which is going to even more decrease the angle between those atoms. So the more repulsion you have, basically the more lone pairs you have, the smaller the bond angle. You do have to be really careful when you get into the expanded octets that you are being careful to separate or consider separately the planar atoms as opposed to the axial atoms. Because although the axial atoms can affect the planar atoms if there's an overall repulsion, it is also possible for the repulsion to cancel out and the angle be a little different, or in this case, even when they're evenly balanced, or a little more affected if it's unevenly balanced.
Let's look at a couple of examples. First, we have BF3. Boron is an exception to the octet rule. It would want an incomplete octet. So in this case, the 3 single bonds are the only charge centers. So an atom with 3 charge centers would be based off the planar triangular shape or trigonal planar shape. So those bonds would be 120 degrees away from each other. Since they're all bonded to bonded interactions, they would be evenly spread out at 120 degrees. Now let's look at SO2. It does have a double bond, but notice it leaves a lone pair on the sulfur. So that would be a total of 3 charge centers: a lone pair, a single bond, and a double bond. But since there is a lone pair, there would be some pushing on the bonded pairs of electrons. So although the basic angle would normally be 120 degrees, those lone pairs are going to decrease that angle. So it is bent with a less than 120 degree angle. Now let's look at water, which is also bent. However, since it has 2 lone pairs, the angle will get even smaller. What I would typically write for this would be way less than 109.5 degrees. You don't necessarily have to memorize the 104.5, but you should know that it is way less than 109.5. Now let's look at Bf4 minus. This ion would have 4 bonded pairs of electrons, 4 charge centers, all bonded to bonded interactions. So that would be a tetrahedral shape with a standard angle of 109.5 degrees. In our last example, ammonia, we have 3 bonded pairs of electrons and a lone pair. So we have 4 charge centers, so we're basing this off the tetrahedral shape. However, because one of them is a lone pair, we're only going to name it based on the atoms, so it's the pyramidal shape, or better yet, the trigonal pyramidal shape, since now we have a square pyramid too. Trigonal pyramidal shape would have a little more repulsion coming from that lone pair, and so the standard bond angle of 109.5 is decreased. So you should know that it is less than 109.5, or to be more precise, it's actually 107 degrees. Now that we know way too much about a molecule's structure, I want to talk about the molecule's polarity. So first, let's review bond polarity. To determine if a bond is polar or nonpolar, all comes down to the difference in electronegativity. If I have 2 atoms that are attached that have identical electronegativities, that bond would then be nonpolar. There is no difference in electronegativity between the 2 hydrogens, so those 2 hydrogens would evenly share the shared electrons. One atom wouldn't hoard it more than the other, so that would be a nonpolar bond. A polar bond can only exist if there is a different electronegativity, because that will create unequal sharing of electrons. In the case here, fluorine is more electronegative than carbon. Therefore, fluorine would hoard the electrons more often than carbon, making that the partially negative side of the molecule, and carbon then by default would be a partially positive side of the molecule. You may recognize the symbols used for partial charges. That's the lowercase delta. Capital delta would be the symbol used for change. So think of this as less change or partial change in the charge. Just knowing if a bond is polar or nonpolar is not enough to figure out if the molecule itself is polar. For that, you have to consider the shape or the geometry, and you have to consider whether the polarity of the bonds will cancel each other out or whether they will add up to make the entire molecule polar. Whenever that happens, where you do end up with an entirely polar molecule, it's nice to use an arrow to show where the electrons would be funneled. In the case of hydrogen and fluorine, fluorine is more electronegative, so this arrow shows the electrons would be moving mostly towards the fluorine. The fluorine would be the partially negative side of the molecule, and the hydrogen would then therefore be partially positive. There are a couple of shapes where the polarity of the bonds can actually cancel each other out. Linear is one of those shapes. Trigonal planar is also a shape in which the polarity could cancel out. And also tetrahedral. We could have all of the polarities going towards or all of the polarities going away from the central molecule. And since we know the bond angles are even, we know that that would then completely cancel out. You do have to be careful though, especially with tetrahedral. If even one of these atoms is a different atom than the other three, chances are it is not going to cancel out. We're just saying that these three shapes have the possibility for the bond polarities to cancel out. There are also some shapes that make it impossible for the polarities to cancel out. The bent or V-shaped is one of those options. The pyramidal shapes will also fall in this category. It makes it impossible for these angles to line up in a way that the polarities would cancel. There is no opposing force in at least one of the vectors. Determining molecule polarity is basically vector addition. You have to consider the forces from all different angles. If the forces seem to cancel out, if the bond polarities go in exactly opposite directions, then it is balanced and therefore nonpolar. If they are going in different angles, if there is no way for them to cancel, then we have a polar molecule. Let's end with some examples determining polarity. First, we have HF. Fluorine is more electronegative than hydrogen, so that would be a polar bond. And as the only bond, that would of course indicate a polar molecule. Water has a bent shape. This is important because it means that the bond between hydrogen and oxygen is not directly opposed to the other bond between the other hydrogen and oxygen. So even though oxygen is more electronegative than hydrogen, so that the bonds would be going both in towards oxygen, the lone pairs put them at an angle. We now know this would be way less than 109 degrees, or actually 104 degrees. So since that is at an angle that does not cancel, the entire molecule is polar. And so you get this upward polarity going basically towards the lone pairs, making the oxygen the most electronegative part of the entire molecule of this polar molecule. Even though carbon is attached to two oxygens, just like the oxygen was attached to two waters, carbon dioxide actually only has two charge centers. Notice the lack of lone pairs on the carbon. So that's going to allow the molecule to straighten out, making this linear shape. So when that happens, we can consider the polarities and to see if they cancel. Oxygen is more electronegative than carbon, so the bond polarity would be going towards the oxygen or evenly away from the carbon. Therefore, there is no net polarity, and we call this molecule nonpolar. CCl4 has our carbon attached to four chlorines, four charge centers with even bonding because there's all bonded to bonded interaction. So we know this would be an even 109.5 degrees exactly between all of the chlorine carbon chlorine connections. So since that's an even connection, even though chlorine is more electronegative than carbon, it would be pulled out in from the same way. It would balance out. And so again, there is no net polarity, and we call this molecule nonpolar. In our last example, we have CH3Cl, meaning one of the attachments is different from the others. This means that the polarities may not evenly cancel out. Now, technically speaking, hydrogen is less electronegative than carbon, so this bond polarity would be going from the hydrogens into the carbon. However, actually, they are more similar in electronegativity than you would think, so much so that generally we actually consider this bond to be nonpolar. So really the only polarity that I'm super worried about is the bond between the carbon and the chlorine. The chlorine being much more electronegative than the carbon would pull the electrons towards the chlorine with a net polarity of the carbon towards the chlorine.